Okay, so we've started talking about the mechanism, about carbonyl chemistry. We'll talk today about addition to carbonyl, the mechanism and the equilibrium constant, about protecting groups, a little bit of NMR review at the end if we have time, and if we really have time, a little bit about the next topic, which is oxidation and reduction, as it involves carbonyl groups and electron transfers. So last time we took an overview of basic carbonyl reactivity, right? That you can have addition. You can have addition where the nucleophile attacks, that's the old Berge-Dunit story, and then the acid A comes on to oxygen and you complete it. Or you can do it the other direction. You can start with the acid protonating the oxygen first, or whatever acid it is, and then to give a oxygen cation that's stabilized by the double bond. You can draw a resonance structure with plus on carbon, and the nucleophile comes in. So there are two ways of doing it. Initially with a nucleophile, initially with an acid, right? And we saw that if you have an alpha hydrogen, then it's possible to pull it off with base to make an enolate and put it on back on the oxygen, right? So that's, you can do an allylic rearrangement to an enol. It can be base catalyzed via the enolate. It also could be acid catalyzed. You could first put the proton on the oxygen and then take it off the alpha carbon, okay? You can also, because of having that functionality, enolate an anion at the alpha carbon or the double bond of the enol. You can also do alpha substitution. So we'll see examples of that. And if you have a leaving group, the thing is called an acid derivative, right? And you can replace it by a nucleophile in a two-step reaction. First add to the carbonyl, then remove the nucleophile. So nucleophilic substitution of acid derivatives. And in the case of carboxylic acids, right, you can have addition, of course, just as we did before. You can have substitution at carbon, where you make a new carbon-oxygen bond, or you can have substitution at oxygen, where you make a new OR bond, right? And again, if you have an alpha carbon, it's possible to do substitution at the alpha carbon, and we'll see examples of that. Now, one particular example is what's called Fischer esterification, which was invented, you'll not be surprised to hear, by Emil Fischer, right? And it's substitution at carbon of a carboxylic acid to convert it into an ester, right? And it's acid catalyzed. So let's think about how this works. Where's the acid going to come in and protonate this? Carl?
The oxygen.
There are two oxygens.
Oh, the oxygen that's connected by a single bond.
How do you know? Why should it do that one? Why not the other?
Because water is a good leaving group, and so that O, just put the H, or you put the proton on.
I'm not asking you what's a good leaving group. I'm asking where the best place to protonate is.
Well, that O has the unshaded, a couple unshaded pairs.
How about the oxygen on top?
That also has unshaded pairs. So
let's look at what would happen if you brought the proton in on top. You'd get that cation. Okay? Anything good about that one that you can't have if you protonate the bottom one? Anybody see?
Resonance.
Debbie?
Resonance.
You can get resonance stabilization of that one. Why protonate this one instead of that one? Well, notice in the starting that this unshared pair is stabilized by that, right? By the low LUMO next door. So that makes it a little harder to protonate, right? On the other hand, the one that's up here could be a lower energy one if it were in those Rabbity or SP square orbitals. So that would suggest that this one might be better, right? But it's killed by that. And when you protonate, but notice the stability you get there gets even more so when you protonate on the top, right? Whatever stabilization you had of this unshared pair before you protonated it, you have more now because you have a lower LUMO to stabilize it. So you get that special stabilization, which you can draw by a resonance structure, that resonance structure. Okay, so you in fact protonate the top, not the bottom. Okay? So once you've done that, then you can bring in an alcohol and attack the carbon. It's going to be easy to attack now since it's a very low LUMO. And then so you get a tetrahedral intermediate. You started with a trigonal carbon, 3 atoms attached to it. Now there are 4, it's a tetrahedral intermediate. So notice that as opposed to SN2 substitution, this one first does an addition, right? And then loses the leaving group. They're not both happening at the same time. So and that's, in that sense, it's analogous to nucleophilic aromatic substitution. Here's a nucleophile that comes in, forms a tetracoordinated carbon, and then this one is going to leave. Here, the amine came in, formed a tetracoordinated carbon from the one that had only 3 things when the fluorine was down here, right? And now this is strictly analogous to that. What we do next is lose a proton from here, and then lose the fluoride, right? Here we're going to lose a proton from here, and then lose hydroxide. So we lose the proton. Now, of course, there's an easier way than losing hydroxide directly. Now you can do what you want to do, Carl.
I want to bring on the proton to the oxygen.
To that oxygen, to your favorite oxygen there, right? Now you've got the leaving group. But the first protonation was up here, and you went through that tetrahedral intermediate. It wasn't a case of making this a leaving group and then doing something like an SN2. You first did an addition to the carbonyl, and then eliminate the water, and of course the proton then comes off again. Okay, so that's the mechanism of Fischer esterification, and of course you can run it either direction. You can run it forwards or backwards. It's a way of replacing OR on the acid carbon, the carbonyl carbon, and you can do it with where R is H as well as where R is some alkyl group. So you can go either way, trading them back and forth. So the way you decide to get ester rather than getting acid, which way are you going to go, is to have a lot more alcohol than water there. So you drive the equilibrium one way. If you turn it around and have a lot more water than alcohol, you'll drive it the other way. Okay, so that's Fischer esterification. Now, Victor Meyer, we saw last time, is the short-term supervisor of Moses Gomberg. And remember what Gomberg did in his lab? He made tetraphenyl methane, right, which was hard to make because it was so sterically hindered, as we found out in trying to make it with models last time. But in fact, it was Victor Meyer who introduced the idea of steric hindrance in 1894. He wrote, "The source of this behavior is stereochemical, the space filling of the neighboring groups." So this was something else that was added to the organic model in the 19th century that we didn't really discuss last time. We discussed configuration, things involving arrangement in space, right, which was Van't Hoff in 1874. We talked about strain, ring strain, that was Bayer, 1885. And we talked about conformation, which Sachse tried unsuccessfully to introduce into the discussion in 1891. But Meyer had the idea of steric hindrance. And he said the source of this behavior, what was this behavior? What was it, the basis of his proposing steric hindrance? It was Fischer esterification in the situation where it doesn't work, right? So it doesn't work for 2,6-dimethyl benzoic acid. When you have a methyl group here and a methyl group here adjacent to that, then you can't do Fischer esterification, right? Now, why not? You can clearly start out here by bringing in a proton and putting it on there, no problem, right? Where do you get into trouble? Do you see? Carl, try again.
When you're gonna bring in the OR group, because it's gonna have to attack from like that way.
It's gonna have to come in from here where this thing is. And you're gonna try to make that into a tetrahedral carbon with 3 extra substituents on it, right? So it's gonna have it's gonna have whatever just came in, right? Some OR group, plus this one protonated and this one protonated, right? So you got to get all these 3 things here where that's not an H, right? That's whatever just came in, right? adjacent to these two things, and it's quite crowded, as you can see here, that there's going to be strain involved in these things running into one another. So you can't get to the tetrahedral intermediate of the fissure esterification. And this was actually the basis of the first suggestion that there was such a thing as steric hindrance. Okay, so this tetrahedral intermediate is hard to make if R is really big and crowded, okay? But there's a way to make the ester nonetheless. And it was invented by a guy who sat in some of your seats. I don't know which seat he sat in when he was a student here, because it was a long time ago. So we can't do that. We can't do fissure esterification that way. But Melvin Newman, whose picture we showed last semester, figured out in 1941 how to do this. And he did it by putting the acid into concentrated sulfuric acid, right? Now, what happens when you put it into concentrated sulfuric acid? Carl? So you put it into concentrated acid, it's going to protonate it. Where will it protonate it?
On the top eight.
On the top, right? Wrong again. No, actually, you're right, of course. Yeah, you do protonate it up. If you put it in 100% sulfuric acid, you do protonate it on the top, right? For the same reason we went through before. But once in a while, you were right originally. Once in a while, it'll protonate on the bottom, the one you wanted. And what's good about that?
Good leaving group.
It's a leaving group, right? So in fact, that can now go away, right? Now, of course, it could come back again, right? But in concentrated sulfuric acid, water is all protonated, right? And as long as it's protonated, it can't come back. It doesn't have the high HOMO, right? So in fact, you can make this thing, which is called an acylium ion, right? And now what he does is take this concentrated sulfuric acid and pour it carefully into water, or pardon me, into alcohol, right? So as he pours it into alcohol, it's no longer concentrated sulfuric acid, right? So the acid, so you won't be able to make these things anymore. But alcohol rather than water is the thing that will get the carbon, right? So then that inhibits the reversal, as we just said, and you pour it into ROH, and now the OR traps it, and you'll lose a proton, and you've made the ester. But notice the difference. Here you made it by dissociation followed by association when it's crowded, right? The normal fissure esterification is association and then dissociation. But by doing it in real strong sulfuric acid, Newman figured out how to do this in the very, very hindered cases. Okay, so now hydration of carbonyl groups, which can be done either acid or base. And that was a note to myself, which I forgot to take out. So let's talk about acid-catalyzed hydration of formaldehyde. So I want somebody to help me out on here. Here down at the bottom we have formaldehyde and water. And what I want to do is add to get the hydrate, as it's called, of the aldehyde, right? The diol. That's a hydrate or a gem diol, the two OHs on the same carbon. So how do we do that? Here we have it's acid catalyzed, it's hydration, so we have water, and it's formaldehyde. How are we going to begin here? Mimi, what do you say? It's acid catalyzed, so what's going to happen?
We're going to protonate one of the, you're going to protonate.
So we're going to protonate something.
Yeah.
So far, so good. What are you going to protonate?
But we're starting on that side, right?
Pardon me?
But we're starting on that side, right?
We're going to protonate, where are we going to protonate it?
The carbonyl group?
Where on the carbonyl group? Which atom?
The O.
Okay, good. So we'll bring it down, and we'll bring that on, and now we have that, which is a nice stable cation, right? It's resonance stabilized. Okay, what's going to happen next? You want to keep us going?
Then the O on the H2O is going to come in and attack the cation.
Okay, so that'll come in, attack the cation. So now we got that. And finally, We're getting pretty close to the product. What do we have to do?
You have to deprotonate the OH.
Right. So you just have to lose the proton. Yeah. And if, you know, it doesn't just fly off, and alcohol will take it or something, okay, or water. Okay, so we've done it. Okay, so that's acid catalyzed hydration of formaldehyde. Now, how about base catalyzed hydration of formaldehyde? Need someone to help us here. Lauren, how about you? So what's going to attack what? We got base for catalyst. Notice we got the H plus back again here. It was catalytic, right? Came in at first, then came out again. So OH minus is going to come in at first, come out again. It's base catalyzed. And we got water and we got aldehyde. What are we going to attack with the OH?
Is it going to attack the double bond?
Where will it attack?
So the zone here, like
On which atom? O or C?
the CH,
Pardon me?
on the C.
On the C. Right, this is our old favorite, attacking pi star. Okay, so that'll come down there. Okay, now we got that. But what we need is the hydrate, the gem diol. So what's going to happen next? What do we need in order to get there? To get from here to here, what atom do we need? A proton. Where do we get it?
Water.
From water. It's in base, right? So we're not going to get it from H plus, right? We're going to get it from water. So the water will come down, do an SN2 type reaction at hydrogen, substitution at hydrogen, and we got the product. And hydroxide, which comes back and catalyzes another one, lives to fight another day. Okay, so either acid or base catalyzed schemes will work for that. Now, how about independent of which catalyst you use, there's going to be an equilibrium constant between water plus the aldehyde and the diol, the gem diol, the hydrate. And as luck would have it, for acetaldehyde, the one which has CH3 and H on the carbonyl, the equilibrium constant is 1. And now we're going to see how that equilibrium constant changes as we change what kind of aldehyde or ketone we're dealing with. Okay? So suppose we have formaldehyde. I want someone to predict for me whether this equilibrium constant is going to be greater than 1 or less than 1. Can anybody see any factors that will be relevant? Alex, can you see a difference? We want differences between this and this, or between this and this, that it's going to make one or the other more stable and therefore change the equilibrium constant.
Well, I guess the top right one might be hindered with the metal.
Aha, that's a good point. This angle gets smaller here, right? So this CH3 could run into the H, but also the CH3 gets more crowded because we got 2 O's on here now. So that's a good point, but it's the one that I've animated second. Okay, which way is that going to change it? Is it going to make the equilibrium constant greater or less than 1?
That'll make the bottom one higher than one.
It'll make this one less energetic than that was, right? Lower in energy. So that'll tend to shift it to the right. Okay. Any other factors? How about anything on the left? Anybody see anything there? Between this and this? Notice that here we have an sp squared bond to carbon, and here we have an sp squared bond to hydrogen. Carl?
Would the methyl be more electron withdrawing?
Generally, carbon is considered donating, but that's not the factor. Right? The strength of bond, remember the strength of the carbon-carbon bond depends on hybridization. The strength of the carbon-hydrogen bond depends on hybridization. But the carbon-carbon bond is more sensitive to hybridization, gets stronger when you go sp squared, than the carbon-hydrogen does. So this one was a stronger bond than that one, with respect to the sp squared hybridization, right? So that made this one low, and this one was high originally because of sterics, as we said. Now we've got, this one is now higher, and this one is lower. So it should shift it to the right, and indeed, both the bond strength that we just talked about and the steric hindrance, right, both suggest that it should shift to the right, and it does. It's 20,000, the equilibrium constant. Now let's try this way. Let's look at acetone, 2 CH3s. Now what do you think? How about on the left? Is this going to be better or worse than before, than the ones above? OE?
It has more bond strings.
It's got 2 of these carbon-carbon bonds that are especially strong. So this is good on the left. How about on the right?
There is more steric hindrance.
Right, there's even more steric hindrance, right? So that one should go to the left from 1. And in fact, it goes the other way, right, by a factor of 2,000 or 1,000 roughly. Okay. Now let's look at this. Let's put chlorine on the methyl group on top, right? Now, does anybody have any ideas about that? So the fact of the chlorine will change this bond. It'll also change that bond, right? Because it's electron withdrawing. So where can it withdraw electrons better from? Can it withdraw electrons better from an sp squared or from an sp cubed bond? Where does it withdraw better? Cassie, you got an idea? Which is the more likely to donate electrons? sp cubed or sp squared? Which one is going to hold the electrons tighter? Right, the one with more S will hold tighter and not be willing to give them up. So if chlorine wants to get them, it's going to get them better from here than from here. So it should shift the equilibrium in that direction. So the electron donation, and it shifts it not nearly by factors of 1,000, but by a factor of 37, okay, compared to when I had an H instead of a chlorine. Now, suppose we have 3 chlorines. Obviously, the same direction should happen, but how big should it be? Sebastian, you got an idea? If 1 chlorine did 37, a factor of 37, so it changed the free energy difference enough to make a factor of 37, right? What should 2 more do? What should 1 more do? Suppose we just put 1 more in. By what factor should we increase it, do you think? Bear in mind that if you make the same energy change, right, because it's in an exponent for an equilibrium, the energy, right, it's a certain factor, right? Because if you add things in exponents, it's like multiplying things, right? So if 1 changes it by 37, the second one, if things are simple, would change it by a factor of 37, and the third would change it by another factor of 37. So if we go all the way from 1 to 3, by what factor should we increase the equilibrium constant? 37 squared. Is everybody with me on that? Okay. Now, 37 squared is a little bigger than 1,000, right? And look at that, it's 28,000. That's better than we had any reason to expect, okay? But it makes sense. And finally, what if we have benzene as the substituent? So benzaldehyde, right? Is that going to shift it right or left? What do you think? Arvin, do you have an idea? Where will the phenyl be stabilizing things more, on the right or on the left?
Probably on the left.
Why?
Because there'll be more resonance with the
Right,
carbonyl.
because you're going to have homo-lumo interaction between the carbonyl and the pi system of the benzene ring. So it should shift things to the left. Conjugation should stabilize the aldehyde, and in fact it does. It's a factor of 100, right? Instead of 1, it's 0.01, so it shifted it to the left. So all these make sense in terms of what we understand of what controls molecular energy. Okay, now, acetal formation happens only with acids. And I think that this is the one. Oh no, okay, yeah, okay, now. So let's look at acid-catalyzed hemiketal formation from formaldehyde. This is closely related to a slide that I just showed you, okay? So what we have is we want to get from the aldehyde to this, right? A hemiketal, right? And it's acid catalyzed, ROH is going to add to this. And how's it going to happen? Well, let's not mess around here, right? Let's just go there, okay? So we protonate just as we did last time when we were adding water, right? Alcohol comes in, forms the bond, bingo, we lose the proton. It's catalytic, right? And we have the product. Okay, nobody's surprised by that. I'm belaboring this, I realize. We did the same thing last time, essentially. Or we did the reaction going the other direction, now I'm going back. But it's really important that you get this. Okay, now, base catalyzed. We can do this just like with water, right? We bring that in, attack the pi star, get that. It takes a proton this time from alcohol instead of from water. And we have the hemiketal, so fine, okay? But suppose what we wanted to do was get the ketal, not the hemiketal, okay? Now notice that that proton can attack either oxygen. It could either protonate OR, in which case what would happen if you then broke a bond? You see where you're going? If you protonate OR and then break the bond between O and C, have alcohol leave. Amy?
Go back to formaldehyde.
Yeah, you're going right back where you started. But you can protonate this one as well as that one. So if you protonate this one and lose water, right, then you instead of reversing, you can continue, right? So you lose water and you get that stable cation, just like this stable cation, except it has an R on it instead of the H, right? And then you bring another alcohol in and do your trick, and you got the full ketal. Fine. We talked last time, spent a lot of time going from the ketal back to the carbonyl. Now we're just going the other direction, reversing all of them. Now let's try to do the same thing with base catalysis. Is it going to work? What's the first step going backwards for base catalysis? If we want to start from here and go backwards, what's the first thing that happens? Linda? The base will pull off the proton, right? Here, the acid could protonate either oxygen. But here, when the base has to pull off a proton, there's only one to pull off. It can't pull it off from the R. And you can't do an SN2. Pulling the R off would be like doing an SN2 reaction where hydroxide attacks the R and this O leaves. But that's a terrible leaving group. That's not a good one, right? So it can only take... So the ethers are inert to base. They don't undergo SN2 reaction. So it can only reverse. It can't go on, right? So you can get a ketal by acid catalysis, but you can only get a hemiketal with base catalysis, right? And furthermore, not only is there no way to get the ketal, but you can't attack the ketal with base either. Once you've got the ketal, it won't attack with base because you can't attack ethers with the base, right? So it's the old joke, you can't get there from here, right? Base will not do it with ketals, either making them or taking them apart again. Okay, now it relates to protecting groups, and I'm going to do this on the board. If I were talking about pedagogy, I would say it's good for me occasionally to draw these things just so you can see a human draw them rather than have them all animated there. But in fact, I didn't have time to do this last night. So there we go. So let's take this up a bit. So we're going to look at ketals as protecting groups, just a couple examples. There are plenty of examples in the book. Okay. Now a particularly interesting compound is glucose. Which is an aldehyde and an alcohol. In fact, it has many alcohol groups. It's got OH here, OH here, OH here, OH here. Now, remember the ketal, or hemiketal, is formed by reaction of an alcohol with the aldehyde. But now we don't have to add an alcohol. We've got alcohols in there already to react with the aldehyde, right? In fact, we got plenty of them. And the question is which one, right? Now, if we were to react this oxygen to make a ring with this carbon, then how many atoms would be in the ring? How big a ring would it be? It would have the oxygen, 1, 2, 3, 4, 5, 6, 7. It would be a 7-membered ring. 7-membered rings are not so easy to form because they pucker up and things on opposite sides run into one another, right? So that's not so good. Obviously, if you use this one to attack the carbon, it would be a 3-membered ring. That's bad, that's strained. This one would be a 4-membered ring. But this one would be a 5-membered ring. That's not so bad. This one would be a 6-membered ring, and that's good. So let's see how we could do that. If we made hemiketal, we could have C OH, H, C OH, COH, I'll just draw it that way. COH, I'll draw it that way. And now, and down here CH2OH. And now this oxygen has to go to there. So I could draw it this way. But nobody thinks I'm trying to draw what it actually looks like. In fact, it's a 6-membered ring. It would look like a cyclohexane. But just for purposes of showing what's bonded to what, it's often drawn that way. Okay, so that would be a hemiketal, and it's 6-membered ring, 6-ring, and that thing is called a pyranose. When it's a 6-membered ring, right? Now, if it were this carbon, then we would have CHOH, and we'd come down here and we'd have CH2OH, and we'd have OH here, and we'd have CHO here, coming out O here, and we'd have OH and OH, and this would be 1, 2, 3, 4, 5-membered ring. And that's called a furanose. Okay? So it could go either way. And they're reversible too, because we know that with either acid or base catalysis, you can go back and forth between hemiketals and the carbonyl group. Okay, now how could you find out which ring size it is? Well, the way it's actually done nowadays is by NMR. Okay? But in the old days, when they didn't have NMR, they had to do chemical transformations to figure out what was what. So chemical degradation. So one thing they could do would be to treat it with acid and alcohol, say methanol. So acid can protonate an OH and then lose water to leave a cation, right? But it turns out that only one of the OHs reacts much more rapidly than the others. Which one is easy to protonate and lose water so as to generate a stable cation? Okay, if we say we protonated this one, for example, we'd generate a secondary cation. Protonate this one, secondary cation, this one, secondary cation, this one, primary cation. Not so good. This one, what would happen if we protonated that one and lost water? I'll write it down below here. So we had OH, H, this O down here, etc. Suppose I protonated this one and lost water, right? Here is the cation I would get. And then I could bring methanol in to put the oxygen on there, lose the proton from methanol, and I would have made what functional group? If I now have O, instead of OH up here, I have OCH3. Everyone sees how I did that, don't I? It's the same thing we've been doing all the time. You protonate, lose water, put the alcohol on, lose proton. That replaces OH with OR. Why did it do it there and not do it at all these other places? What was specially good about this cation that the others didn't have? Chris? Let me draw I'll draw the cation here, or here. So the cation has an O on it, an H on it, a carbon on it, plus. What's good about, and this one goes down then to the bottom. What's good about that cation, Chris? Pardon me?
Secondary.
It's secondary if you want to consider an oxygen as if it were carbon, but so were all these others secondary, right, if you protonated those and lost water. What's especially good about this one?
You have an electron withdrawing oxygen.
Is that good to make a cation if you have something that's electron withdrawing? That means it's already positive. It doesn't want to get more positive. So the electron withdrawal by the oxygen is going to be bad for this. But there's something that makes it good. Brandon? Right. The unshared pair on the oxygen is stabilized by this vacant orbital, right? You can draw a resonance structure that puts a double bond here and plus on the oxygen. Okay, so this one is the one that's reactive to make a ketal, right? This thing is a ketal. It's got 2 OR groups on it, right? And that one we could make a ketal too, up here, of course, and not the other places. So we can make a ketal, right? Now, it's possible under those circumstances to do reactions with alcohols, right? To chew up the other alcohols, but not chew up this one, right? Because that alcohol is now in the form of OCH3, right? Well, we're talking about reactions next class, right, that involve reactions of alcohols, oxidation, for example, okay? So this is protecting that particular carbon from being reacted by having a full ketal there. Now, then you can take it apart again by treating it with acid and water, get it back and see what compound you have. Which of the oxygens in that chain got oxidized and which ones were not oxidized? Compare with known compounds, and you know what the size of the ring was. Because notice that this, not only did this group keep, this OH keep from getting oxidized, this OH, that is this OH, didn't get oxidized on this side, right? And this OH didn't get oxidized there. So the protection protects not only the aldehyde from being oxidized, it also protects the alcohol. Professor Ziegler, who we've mentioned, who teaches Chem 220 often, is a synthetic chemist, and always when he teaches a class in synthesis, he always points this out, that people have tunnel vision often. They think of ketals as something that protects a carbonyl. But it also protects an alcohol at the same time that's tied up as an ether and won't do the reactions that the alcohol would do. So you not only protect the carbonyl, you also protect the ROH. And a particular example of that is what's called THP protection. So, so this compound, right, can be reacted with ROH and acid catalysis, right? So how's it going to start out? Derek, you tell us. Where are you going to protonate this?
The O.
You could protonate this O, you could protonate this O, right? Either of them particularly good? There's actually another place to protonate that's very good. Can anybody see? Arvind?
On the carbon-carbon double bond.
Where? Top or bottom?
Bottom.
No. Top. Okay, if we put the H plus here, right? Why is that good? Got the H here. There are now two H's there, of course. There was one there already. What's good about that cation? Matt? Yeah, you could say, that's what everybody always says, that it's stabilized by the lone pair on the oxygen. But actually, what it does is stabilize the lone pair on the oxygen, which makes the molecule more stable. You're right, that's what everyone says, that it's stabilized by the lone pair. But in truth, it stabilizes the lone pair. Okay, so we got this. Now we got ROH. What's it going to do?
It's going to.
John? What's the ROH going to do now when you have that cation?
The low pair on the oxygen will attack it.
And then what?
And then the H will lose.
Yeah, you lose a proton, right? So we got this. And what functional group is this that we now have? Does anybody recognize this functional group? It's familiar. Lee? It's a ketal, right? Two ethers on the same carbon, right? But we didn't make it from a carbonyl. We made it this way, right? Okay, so now we could do reactions. Suppose this R had something else coming off that was going to react, maybe a double bond, and we wanted to react that, but we didn't want to react the alcohol, right? But the ether keeps the alcohol safe, right? We do the reaction down here. Now we need to get the alcohol back again, having done what we wanted to do down here. How are we going to get it back? How can we remove this stuff? We can protonate the O, lose this, generate this nice stable cation again, go back. We just go back and forth, right, with water. This time, go back with water. So we can make, so this is a protecting group for an alcohol, keep it from reacting. I'll mention one other protecting group for alcohols here because they mention it in the textbook that many of you have, which is called TBDMS. It's T-butyl dimethyl silyl. So T-butyl dimethyl silyl, and you start with the chloride, right? Now the chloride has a bond strength, this bond, of 90 kilocalories per mole, right? But you can react it with ROH, and the unshared pair will react to form a bond with silicon, right? So now the silicon has 5 things attached to it, right? But then the chloride can leave. It's not an SN2 reaction, it's an association followed by dissociation, because silicon down in the next row of the periodic table has vacant orbitals that can make a bond with that. Okay? Right? So now we got T-butyl, Si, methyl-methyl, O-R, right? And the strength of the SiO bond is 110 kilocalories per mole. So this is downhill in energy. Okay? Now, so now you can do what you want to do, other things in the R group without it's not an alcohol anymore. It's like a little bit like an ether, right? But the neat thing is that there's a special way to take it apart. You can take it apart by treating it with tetramethylammonium, methyl 4N plus, a salt, but the business end is fluoride, right? Because fluoride can attack the silicon the same way the unshared pair on oxygen did here. And then you can protonate and lose the OR, right? So this is the nice thing, the product from the silicon is now, which you don't really care about, is the SIF, and the SIF bond is a fabulous bond. It's 135 kcals per mole. Right? So plus now your ROH once you've protonated. Right? So the nice thing about this is there's not that many things that react with fluoride easily. It's a terrible nucleophile generally, right? So now you have something that's very selective that will only do that and take this protecting group off and not mess up other things that's in your R group, right? And this was invented in the 1970s by a professor at Harvard who got the Nobel Prize in synthetic chemistry, Professor Corey. So that's those things. And now imines and their derivatives and the role of electron pair repulsion and allylic stabilization. So I'm going to just introduce this here and we'll finish it next time. Okay, so we have a carbonyl and we've been reacting it with alcohols or water, right? But let's consider reacting with an amine, which actually has certain similarity to water, of course. It's got the unshared pair and protons on the nitrogen, the way alcohol has protons on the oxygen. So this can react. And of course that can lose a proton here, and it could put a proton on there. It's probably not the same proton. And this is called a carbonyl amine. What's the analog when you have a oxygen instead of NH in there? What functional group is it? If this were just an O instead of an NH, what would you call this functional group? I see you all bored. It's a hemiketal, right? That's what we've just been talking about. But the carbonyl amine is the amine analog. Now, you can do, because you have this hydrogen here, you can do something special, right? You can lose this OH, say protonate and lose it, helped out by this. And we get this. Right, and water. Okay, pardon me, it would be originally NH plus when we use the unshared pair, but then we can lose the H plus. So now we have this functional group, which is called an imine, right? Which is rather like a ketone, right? So we got rid of the oxygen and replaced it with NR, and the oxygen became H2O by this same kind of stuff we've been doing, right? So these imines turn out to be very important, not only in organic chemistry, but also in biology. And we'll continue with that next time. Or actually, yeah, we'll continue with that, but there'll be no more on the exam on Friday than what we've done today. Okay? Pardon me? Oh, forget the amines, okay? Just do the ketals and hemiketals. The amines will be on the final.